Dear students, welcome to CS Mayura Chemistry classes. So now we are going to discuss Re-Neet 2026, all the 45 questions with in detail solutions. Coming to first question, for the following reaction sequence, choose the correct option. Here, benzene is given. Benzene is given with acetyl chloride, CH3COCl in presence of AlCl3. This reaction is Friedel-Crafts acylation reaction. This is Friedel-Crafts acylation reaction. In Friedel-Crafts acylation, it produces acetophenone. Name of this compound is acetophenone. Now, in the second step, this acetophenone is treated with sodium hypochlorite. Sometimes this sodium hypochlorite will be given as chlorine with sodium hydroxide. So they can give chlorine with sodium hydroxide or sodium hypochlorite. So this is chloroform reaction. Chloroform reaction or iodoform reaction is famous reaction. When iodine with sodium hydroxide is given, iodoform reaction. Chlorine with sodium hydroxide is given, chloroform reaction. Here, to give a positive test, it should have methyl ketone. Acetophenone has methyl ketone group. It will give chloroform reaction. The product is chloroform CHCl3 and the remaining part of the compound gives sodium salt of benzoic acid. Sodium salt of benzoic acid or sodium benzoate. Now, this sodium salt of benzoic acid in acidic medium gives benzoic acid. In acidic medium, it is giving benzoic acid. This chloroform, when it is exposed to atmospheric oxygen, it produces COCl2. What is COCl2? COCl2 is phosgene. Phosgene is a poisonous gas. It is more poisonous than chloroform. So, here options P is the sodium salt of carboxylic acid, correct. But Q is not primary alcohol. Q is not alcohol. This is Q and this is P. P is sodium salt of benzoic acid and Q is chloroform. It is not alcohol. P and Q are aromatic. No, Q is not aromatic. Next, P gives carboxylic acid on acidification, correct. And Q gives poisonous gas on exposure to air and light, that is phosgene, is correct. So, third option is correct. Next one, FeOX thrice 3 minus is chiral. FeOX 3 minus is given as chiral. Whether it is chiral or not, we have to find. This is MAA thrice type of complex having symmetrical bidentate ligand, 3 symmetrical bidentate ligand. MAA3 type of complex is chiral. It is a chiral. How do you say it is chiral? In this complex, no plane of symmetry and no center of symmetry. No plane of symmetry and no center of symmetry. You can see the structures. I am taking the structure of MAA thrice. This is symmetrical bidentate ligand. This is another symmetrical bidentate ligand. This is third symmetrical bidentate ligand. For this mirror image, this is the mirror image of this complex. See, here plane of symmetry is not possible and center of symmetry is not possible. So, they are optical isomers, they are chiral compounds and they are enantiomers. So, MAA thrice type of complexes always chiral because there is no plane of symmetry and no center of symmetry. Now, coming to trans H2O twice, OX twice. Coming to trans. The CR H2O twice, OX twice. This is MA2 AA twice complex. Ma2A twice complex. Take this complex. I'm taking transform. Total coordinates number is 6, octahedral ligand. Transform means they are opposite. Here A. The symmetrical bidentate ligand is also opposite, A. This is transform. So like this you can have a plane of symmetry. Plane of symmetry is possible in this complex. So this is a chiral. This is wrong statement. They have given chiral, wrong statement. So which complex is chiral means which does not have plane of symmetry and center of symmetry, that is chiral. If any complex is having plane of symmetry or center of symmetry, that is a chiral. Now in this, if you take cis form does not have plane of symmetry. I will give you cis form also. Octahedral geometry. Cis form means they are on the same side. Similar ligands on the same side. Here I am taking symmetrical bidentate ligand. Symmetrical bidentate ligand. And here A. It is not possible to draw plane of symmetry. No plane of symmetry because this is above the plane and this is below the plane in opposite directions. So this is chiral. This is a chiral. First statement is correct, second statement is wrong. Next, the following carbocation is stabilized by the interaction of empty p orbital with. So I am taking this compound. So benzene. Here this carbon has positive charge. Expanding this structure. There are 3 alpha hydrogens. Adjacent to the positive charge, the carbon hydrogens. Carbon adjacent to the positive is alpha carbon. This is alpha carbon. These are all alpha hydrogens. There are 3 alpha hydrogens. When there is alpha hydrogen, hyperconjugation is possible. Now I am taking hyperconjugation. Hyperconjugation. At least one alpha hydrogen is there. Hyperconjugation is possible. In hyperconjugation, what happened? This sigma electrons are shifted to here. Here positive charge means vacant p orbital. So they told empty p orbital. This is empty p orbital, vacant p orbital, and the sigma electrons are transferred to here. Then what compound we will get? Here double bond, and this is CH2. After hyperconjugation, we will get compound like this. Next, so here sigma electrons are used in hyperconjugation. Next point is taking benzene and this carbocation. There is resonance. If there is conjugation, resonance is possible. Single, double, single positive charge. So conjugation is there. When there is conjugation, there is resonance. Now these pi electrons are involved in resonance. When these pi electrons are involved in resonance, this compound is, here you will get double bond, and this is CH3, no change in that. These pi electrons are shifted to here, so here you will get positive charge, and these double bonds, no change. Right, now coming to this question. Interaction of empty p orbital with, in hyperconjugation, filled sigma orbital. These sigma electrons are in the sigma orbital. In resonance, pi orbital, filled pi orbital. In resonance, filled pi orbitals are interacted with the empty p orbital of carbocation. In hyperconjugation, filled sigma orbital is interacted with the empty p orbital of carbocation. In potash alum, the ratio of K plus and SO4 2 minus ions. I am taking potash alum. Potash alum formula K2SO4 Al2SO4 thrice 24H2O. It's a double salt. Potash alum formula. We have 2 K plus ions and 2 aluminum ions, and total how many sulfate ions are there? 4 sulfate ions are there. 4 sulfate ions. So 2 K plus ions, 4 sulfate ions. Ratio is 2:4. 2:4 means 1:2. Answer is 1:2. 2. The correct statement about peptides and proteins is, correct statement about peptides and proteins is, tertiary structure of protein has 2 or more polypeptide subunits. No. In quaternary structure, there will be 2 or more polypeptide chains. In tertiary structure, 1 polypeptide chain. Only the proteins having quaternary structure are biological active. Wrong. Wrong. So even with the tertiary structure, there are many proteins with the biological activity. Quaternary structure is not necessary. Third one, in beta pleated sheet structures, peptide chains are held together by intermolecular hydrogen bonds. This is correct. In beta pleated structures, intermolecular hydrogen bonds are there. This is correct statement. In alpha helices, the polypeptide chain is twisted into a left-handed screw helix through intramolecular hydrogen bonding. Intramolecular hydrogen bonding is correct. That helical structure is due to intramolecular hydrogen bonding. That is correct. But it is not left-handed screw. This is right-handed screw. So let us see more details about this protein structure. See, secondary structure. Alpha helix is there, beta pleated sheet is there for secondary structure. Alpha helix means that is stabilized by intramolecular hydrogen bond. These are intramolecular hydrogen bonds. So this alpha helix structure is stabilized by intramolecular hydrogen bonds. Single chain. This is a single polypeptide chain. Right-handed screw, not left-handed. So why right-handed means it depends on the steric constraints. Beta pleated sheet means same polypeptide chain is having intermolecular hydrogen bonds. This is one part of the chain, this is another part of the chain, this is another part of the chain. So these parts are connected by intermolecular hydrogen bonds. In between the molecules is intermolecular hydrogen bond. So these chains extended side by side with intermolecular hydrogen bonds. Now coming to tertiary structure. So in the tertiary structure, here 3-dimensional. This is 3-dimensional. 3-dimensional representation of a single polypeptide chain. Example, myoglobin. Quaternary structure means there will be 2 or more. There are 2 or more polypeptide chains. That representation, that arrangement is quaternary structure. Next, the numbers 17.0145 and 21.0235 were rounded to 3 figures after the decimal point. The resulting numbers are. So there are some rules for rounding of the numbers, rounding of the decimals. 17.0145, we have to round off up to 3 figures after decimal. Means here last number is 5. Here the preceding digit is 4, that is even. So there is no change in that number, 17.014. Here the preceding digit is 3, odd. This is odd. Then we have to add 1 for this. The answer is 21.024. 17.014 and 21.024. This is our answer. So let us have more discussion about this. One number is given, 2.761. We should make it into total 2 digits. 2.761. Here, to make it into 2 digits, see this 6. 6 is greater than 5, then add 1 to 7, 2.8. Next, 2.749 is there, 2.749. Now this 4 is less than 5, then there is no change in that, right? When the preceding digit is greater than 5, add 1, less than 5, don't change anything. Now, if the digit is 5, 1.751, this is 5, not greater than 5, not less than 5, equal to 5. Equal to 5 means this 7 is odd. For odd, you have to add 1, 1.8. Now 3.350, 5 is there. This is odd, add 1, 3.4. 3.450, this is 5. Here even number is there, don't change. When even number is there, don't change. When odd number is there, add 1. This is how we are rounding up the numbers. Next, the correct order of solubility of the given salts in water at 298 kelvins. I am taking silver bromide. silver bromide. In aqueous solution, the silver bromide splitting is Ag plus Br minus. This is S and this is S. Ksp is equal to S square. Ksp is equal to S square. For the first one, S is equal to, S is equal to Ksp whole power 1 by 2. Second one is zinc hydroxide. This is zinc hydroxide. This zinc hydroxide splitting is Zn2 plus 2OH minus. Zn2 plus solubility S, 2OH minus solubility 2S. Stoichiometric coefficient 2 is there, then 2S. Now, for the second one, what is a Ksp? Ksp is equal to S into 2S whole square. This is 4S square into S, 4S cube. Ksp is equal to 4S cube and solubility S is equal to Ksp by 4 whole power 1 by 3. This is second one. Now coming to third one. The third one, salt is Hg2Cl2. Here important point is the Hg2Cl2 splitting is Hg2 2 plus 2Cl minus. We should not write 2 Hg plus. Hg plus is unstable. So Hg2 2 plus 2Cl minus. So this is S, this is 2S, same as zinc hydroxide. Here solubility is also Ksp by 4 whole power 1 by 3. Take this solubility as S1, this solubility as S2 and this solubility is S3. So their respective Ksp values are given. You just substitute their Ksp values. Here in the first case 5 into 10 power minus 13 whole power 1 by 2. Here 10 power minus 5 by 4 whole power 1 by 3. Here 1.3 into 10 power minus 18 by 4 whole power 1 by 3. So by simplifying this we are getting these numbers. S1 is 7.07 into 10 power minus 7. S2 is 6.3 into 10 power minus 6. S3 is 6.87 into 10 power minus 7. So what is our question here? The correct order of solubility of the given salt. Which has more S value, that solubility is more. 10 power minus 7 is less, 10 power minus 6 is more. So S2 solubility is more. This is 7.07 and this is 6.87. Order is same, 10 power minus 7, 10 power minus 7. So S1, next S3. This is our correct order. Among the following options, the correct trend in the electron gain enthalpy. This electron gain enthalpy order, the highest electron gain enthalpy is chlorine among halogens, next fluorine, next bromine, next iodine. So actually they are supposed to give negative electron gain enthalpy. They should give negative electron gain enthalpy. Otherwise, simply electron gain enthalpy means mathematically the correct order is iodine is greater than bromine, bromine is greater than fluorine, fluorine is greater than chlorine. This is the correct order. If the question is simply electron gain enthalpy, negative electron gain enthalpy means this is the correct order. But this option is not there. This option is not there. So then we have to select this answer only. If this option is also given in the question, this will be correct answer. Even in NCERT, line to line, they used to mention negative electron gain enthalpy to avoid the confusion, that mathematical and conceptual confusion. Clearly, they are giving negative electron gain enthalpy. I hope it is clear. Next, for an ideal solution formed by mixing liquids P and Q, delta H mixture is 0 and delta V mixture is 0. So I have two liquids. Here P liquid is there and here Q liquid is there. When we mix these two liquids, we will get mixture of P and Q. In P liquid, we will have PP interactions. In Q liquid, we will have QQ interactions. In PQ mixture, we will have PQ interactions. Now, this is ideal solution. Ideal solution. Ideal solution means these PP interactions and QQ interactions are same. PP interactions and QQ interactions are similar. Then what happens? When we mix these two liquids, how much energy is required to break the existing interactions between PP and QQ? The same amount of energy is released in the formation of PQ interactions. When new interactions are formed, energy is released. When existing interactions are broken, energy is required. So here how much energy is absorbed, the same amount of energy is released. That's why delta H mixture is 0 for ideal solution. In positive and negative deviation, delta H mixture is not equal to 0 because their interactions are different. They may be more or less. Next, coming to delta V mixture, when interactions are when interactions are similar, there is no contraction in the liquid, there is no expansion in the liquid. So then what happens? No change in the volume. When more interactions are coming in the mixture, volume increases, expansion. When less interactions are coming in the mixture, when more interactions are coming, contraction, volume decreases. When less interactions are present in the mixture, less interactions, then what happens? Volume increases, that is expansion. But here similar interactions, no change in the volume, no contraction and no expansion. So delta V mixture is 0, delta H mixture is also 0. Now, no interaction occur between P and Q. This is wrong. Interactions occurs between P and Q. Those interactions are similar to PP and QQ. Let us have more discussion about this. So this is an ideal solution. Delta H mixture is 0, delta V mixture is 0 for P and Q. Okay. So these are the interactions or strength of PP. This is strength of QQ and this is the strength of PQ. All these are similar. PP strength, PQQ strength and PQ strengths are similar. When strengths are similar, what happens here? To break the interactions requires energy. To break the interactions in the P requires energy, in the Q requires energy. Now here, after mixing these two, energy is released. This is exothermic, this is endothermic. Here how much energy is required to break the interactions? Here same amount of energy is released. See, both are equal. Now volume of solution. When they have similar interactions, they are occupying the same volume. So there is no change in the volume. Suppose this is 10 liters. This is 10 liters. And this is what? 20 liters. 10 plus 10, 20 liters. Same interactions are there. When more interactions are there, this volume will be less than 20 liters. When less interactions are there, this volume will be greater than 20 liters. Next, the amino acid that gives a red blood color on treating its sodium fusion extract with sodium nitroprusside. Who will give red blood color with sodium nitroprusside means organic compound having both nitrogen and sulfur. General organic compound means there will be carbon, no need to specify that. In addition to the carbon, if there is nitrogen and sulfur, it will give sodium nitroprusside. It will give red blood color with sodium nitroprusside. This is methionine. In methionine, we will have sulfur and nitrogen. Sulfur and nitrogen. So because of this sulfur and nitrogen, this methionine gives red blood color with sodium nitroprusside. Let us see more discussion about this. So when there is only sulfide, only sulfur is there is no nitrogen, then that organic compound is treated with sodium fusion extract which contains sodium sulfide. It has sodium fusion extract, it contains sodium sulfide. Now add reagent. What is our reagent? Sodium nitroprusside. Then violet color you will get. When there is only sulfur, violet color complex will get. That complex is FeCN5NOS. Now if there is nitrogen also, along with sulfur, nitrogen is there. In sodium fusion extract, what we will have? Sodium thiocyanide, NaSCN. And when it is treated with ferric chloride, it gives red blood color. This NaSCN from the sodium fusion extract treated with ferric chloride, not sodium nitroprusside. It is treated with ferric chloride. What it is giving? Red blood color. Right. I am giving two important examples here, cysteine and methionine. In cysteine, the sulfur is in the form of thioalcohol, SH, thioalcohol form. It is free and easy to extract that sulfur. Okay. Now this is treated with sodium nitroprusside. Immediately it will give red blood color, deep red blood color. But when we take methionine, methionine is in the form of thioether. Here it is difficult to extract this sulfur. So when sodium nitroprusside is added, first it will give yellow color. Immediately it is not giving red blood color, first it is giving yellow color in alkaline solution. When this solution is acidified, then it will give red blood color. Right? In cysteine, sulfur is free, therefore immediately it is giving the red blood color. In methionine, sulfur is not free, first it is giving yellow color with sodium nitroprusside. After acidification, it is giving red blood color. So this is one very important example. Standard electrode potential E0 for the half cell reaction. Fe3 plus electron gives rise to Fe2 plus at 298 kelvins is. Now they have given two potentials, Fe3 plus to Fe. Make it into equation. First equation, Fe3 plus 3 electrons gives rise to Fe. What is the potential for this? Minus 0.04 volts. And second equation, I am using this Fe2 plus 2 electrons gives rise to Fe. And for this reduction, what is the potential? Minus 0.44 volts. And what they asked, this reaction potential value, that is third reaction, Fe3 plus electron gives rise to Fe2 plus. What is the standard potential of this reaction, third reaction? How do you get this third equation from 1 and 2? Left side we have Fe3 plus, right side we have Fe2 plus. So take 1 minus 2. This 1 minus 2 gives 3. 1 minus 2 gives 3. So directly we should not take their potentials for addition and subtraction, because potential is intensive property. Potential is intensive properties, direct addition and subtractions we should not do. So we have to use the extensive property, that is Gibbs energy. Delta Z1 is an extensive property. First reaction Gibbs energy is delta Z1, second reaction Gibbs energy is delta Z2, third reaction Gibbs energy is delta Z3. So delta Z1 minus delta Z2 is equal to delta Z3. So we know the formula for Gibbs energy change, that is NFE minus N1FE1 minus of minus plus N2FE2, that is equal to minus N3FE3. We have to find this E3. F is Faraday's constant, common for all, cancel it. Then what we will get? Minus N1E1 plus N2E2 is equal to minus N3E3. Now N3E3 is equal to, multiply with minus, that is what? N1E1 minus N2E2. Now E3 is equal to N1E1 minus N2E2 by N3. Here N1 value, number of electrons involved in the first reaction, N1 value is 3. So E3 is equal to N1, number of electrons in the first equation, 3. What is its potential? Minus 0.04. Minus second equation, how many electrons involved? 2 electrons involved. What is its potential? Minus 0.44 whole divided by N3. In the third equation, how many electrons involved? 1. Simplify this. So if we simplify this, we will get answer plus 0.76 volts. In an acidic medium, 10 ml of 0.25 molar oxalic acid is titrated with the KMnO4 solution. Here KMnO4 solution is titrated with oxalic acid, H2C2O4. The main products are KMnO4 self-reduced to Mn2 plus, oxalic acid is oxidized to carbon dioxide. Here manganese oxidation state is +7, this carbon oxidation state +3, this carbon oxidation state +4, right? +7 to +2, N factor is 5. In oxidation reduction reactions, N factor is change in oxidation state into atomicity. +7 to +2, difference in oxidation state is 5 and 1 manganese, so 5 into 1, 5. Oxalic acid N factor, +3 to +4, difference is 1. 1 into 2, 2 carbon atoms. 1 into 2, 2. Here N factor is 2. Now, given data I am writing. Oxalic acid data 10 ml and 0.25 molar. 10 ml, 0.25 molar. Potassium permanganate data is what? 10 ml. What is its strength? In options, molarity is there. We have to find the molarity. So generally, titration problems better to solve with normality. Don't do with molarity, you will be confused. And to solve this question with molarity, we need a balanced equation. All chemical equations, you can't write balanced equations. So that's why follow equivalent concept, that is normality concept. To avoid the requirement of balanced equations, we are using normality concept. So first I will find the normality. After that, we can convert that normality into molarity. So here, normality formula N1V1 is equal to N2V2. What is normality? Normality is equal to molarity into N factor. Substitute N1. I will take KMnO4 as 1, oxalic acid is 2. So its molarity we have to find. M1. What is its N factor? 5. What is its volume? 10. Normality of oxalic acid, its molarity is 0.25. What is its N factor? 2. And its volume is 10. This 10 cancel. 0.25 into 2, 0.5. Then M1 is equal to 0.5 divided by 5, that is 0.1 molar. Molarity of KMnO4 is 0.1 molar. According to crystal field theory, the correct order of ligands with respect to decreasing order of field strength. This is direct question from spectrochemical series. The spectrochemical series belongs to crystal field theory concept. The strong ligand is CO, next strong ligand is ammonia, next strong ligand is water, next strong ligand is Cl minus. So this spectrochemical series order is very important. And one logic is here, in spectrochemical series, carbon donors strength is, ligand field strength is more than nitrogen donors. Nitrogen donors ligand field strength is greater than oxygen donors. Oxygen donors ligand field strength is greater than halogen donors. Generally, it follows this order. So there are so many concepts we will discuss in coordination compounds. 2 moles of an ideal gas undergoes free expansion from 10 liter to 100 liters, value of delta S system and delta S surroundings. This is an ideal gas, and remember there is free expansion. Change in entropy of a system formula 2.303 nR log V2 by V1. This is our formula. Then 2.303 into n value 2, R value not substituted here. Then final volume is 100 liters, initial volume is 10 liters. V2 is final volume, V1 is initial volume, R is gas constant, N is number of moles. 10 times log 10 is 1. This is 4.606 R. This is delta S system. Now I want delta S surroundings. So delta S surroundings is equal to minus Q by T. For free expansion, heat change is 0. For free expansion, heat change is 0. 0 by something, 0. So let us have more discussion about free expansion. So free expansion of ideal gas. Q is 0. Work is 0. In free expansion, work done is 0. There is no opposing force, then work done is 0. And change in internal energy is 0. We have a formula, delta E is equal to Q plus W, first law of thermodynamics. In free expansion, work done is 0. And heat change is also 0, no heat change. Then change in internal energy is also 0. When delta is 0, delta H is also 0. Del H is equal to del U plus P delta V. This is 0. Work done also 0. Then delta H is also 0. So what are the other characteristics for free expansion? Isothermal process, temperature is constant. So delta T is 0. So this is for free expansion. Delta H is 0. And this is irreversible process. Free expansion is irreversible process. Spontaneous process. Once the process is started, it will be completed. It won't stop anywhere. And entropy change, delta S surroundings is 0. entropy change of the surroundings. Delta S surroundings is 0 and entropy of the total entropy change is positive because it is spontaneous. One of the spontaneous condition is delta S total. Delta S total is 0. When delta S total is positive, spontaneous, negative, non-spontaneous equal to 0, equilibrium. 2A plus B is a zero order reaction where K is 1 mole liter inverse minute inverse. Initial concentration of A is 2 molar. Then the time taken to complete 75% of the reaction will be. Now, given reaction is zero order. That reaction is 2A plus 2A gives rise to B. That rate R is equal to K into concentration of A power 0 because it is zero order. The rate is minus 1 by 2 delta A by delta T is equal to K into A power 0 is what? 1. Now, this delta A by delta T is equal to minus 2KT. Minus 2K. This is minus 2K. Delta A means final concentration A, initial concentration A naught, and final time, that is what? T 75% minus T naught is equal to minus 2K. So here K value is given, K value is 1. Initial concentration is 2 molar. Then the time taken to complete 75%. A naught value is 2 molar. And A is what? A is what? The concentration left after 75% completion. 75% is completed. And remaining how much is there? 25%. 1/4. 2 into 1/4. That is what? 0.5. So initial is 2 molar, 75% is completed, remaining 0.5. Now 0.5 final, initial 2 divided by T naught is 0 initial, T 75% is equal to minus 2 into 1, K value is 1. Here 0.5 minus 2, that is minus 1.5, both sides minus cancel, then T 75% is equal to 1.5 by 2. 1.5 by 2, that is 0.75 minutes. First statement, generally 3D transition metals have high melting points, correct. 3D transition metals have high melting points, that is correct. Why? The involvement of 3D electrons in addition to 4s electrons in the interatomic metallic bonding. This is also correct. 4s 3D. In transition metals, 4s and 3D energy difference is less. So actually valency shell is 4s. But due to less energy difference, this 3D electrons also involves in bonding. So more number of valence electrons involved in metallic bonding, then it increases the strength. Obviously, their melting points are also higher. For a salt XY, which is a strong electrolyte, so this question is based on Debye-Huckel-Ansauger equation. That is what? Delta M is equal to delta M naught minus B root C. This is Debye-Huckel-Ansauger equation. What is given here? The salt is XY. Salt is XY. The salt XY will have cation X plus and anion Y minus. Keep it in mind. Slope is 90, minus 90. So let us rewrite this equation. Lambda M is equal to minus B root C plus lambda M naught. This equation is similar to Y is equal to Mx plus C. Then what is the slope here? Slope M is equal to minus B. Slope M is equal to minus B, that is minus 90. This is what? Minus B, minus 90. Next, what is given? So this is the plot for lambda m and root c. Lambda m and root c. Here lambda m and this is root c, negative slope and positive intercept. Graph is like this. So slope is minus b. That is minus 90. Next, this concentration is what? Concentration C is 0.01, 10 power minus 2 molar. Lambda m value, lambda m is given, that is 145. What is the limiting molar conductivity of Y minus ion? Lambda m naught of Y minus they asked. Lambda m naught of Y minus. So use this equation. Lambda m is given, that is 145. That is equal to lambda m naught. We don't know, we have to find it. Remember, this is lambda m naught of xy, not x plus, not y minus, this is xy. Minus b. What is that? Minus 90. Next, root c, square root of 10 power minus 2. So this is 145 lambda m naught minus root 10 power minus 2 means that is 10 power minus 1 minus 9. Now lambda m naught is equal to 145 plus 9. 145 plus 9 means that is 154. This is lambda m naught of xy. So lambda m naught of xy is equal to lambda m naught of x plus lambda m naught of y. This value is 154 and this x plus value we have to find lambda m naught of x plus and y minus value is x plus value is given 74 and this value y minus value we have to find lambda m naught of y minus. Now this is 154 minus 74 equal to 80. So the amount of carbon dioxide evolved upon complete combustion of 116 grams of N-butane. Any butane formula C4H10. When it burns with oxygen, it produces carbon dioxide and water. Balance is equation, 4 carbons, here 4 carbons and 10 hydrogens. This is 5H2O, 10 hydrogens. Now oxygen balancing, 4 2s are 8, 8 plus 5, 13. Then I will take 13 by 2 oxygen. 13 by 2 O2 means 13 only. Now 116 grams of N-butane is there. How much carbon dioxide is evolved? So butane molecular weight, 4 carbons 48, 10 hydrogens 10. This is what? 58. 58 grams of butane is producing 4 into 44 grams of carbon dioxide. Then 116 grams of butane produces how much carbon dioxide? That is 116 into 4 into 44 divided by 58. 58 in 116, 2 times. So the simplified value is 352 grams. For an elementary chemical reaction, the Arrhenius plot is given below. So one graph is given. Here activation energy is 6.64 kilojoules. R value 8.3 into 10 power minus 3 kilojoules. Take kilojoules. Here joules given into 10 power minus 3 kilojoules. And rate constant K is equal to E square. Arrhenius equation, one of the formula, that is K is equal to A into E power minus EA by RT. Ln K is equal to ln A, this is cancel, E cancel, minus EA by RT. So ln A means base E, log means base 10, ln means base E. Substitute the known data. K value, ln base E, K value is what? E square. And ln A, this is what? Intercept. This is intercept. What is the intercept from the graph? Positive intercept, that is 6. 6 minus activation energy 6.64 divided by R value 8.3 into 10 power minus 3 and temperature we have to find the temperature. We should find temperature. Now this E base E cancel, that is equal to 2 ln E cancel 2 is equal to 6 minus 6.64 by 8.3 into 10 power minus 3 into T. Simplify this, we will get T 200 kelvins. By simplifying this, we will get T value 200 kelvins. Heating NaCl with concentrated H2SO4 and MnO2. NaCl with manganese dioxide in presence of sulfuric acid. It is an oxidizing agent. It oxidizes the NaCl into chlorine, and byproducts are MnSO4, Na2SO4 and water. So what is produced here? Chlorine gas is produced. This is an oxidizing agent. Results in oxidation of manganese. No. MnO2 is reduced to MnSO4. Here manganese is +4. This manganese is +2. +4 to +2 reduction. NaCl is oxidized. Manganese dioxide is reduced. Second statement. Heating NaI. Same reaction. Sodium iodide with manganese dioxide in presence of sulfuric acid. This mixture is oxidizing agent. Then we will get I2, MnSO4, sodium sulfate and water. Here sodium iodide to iodine oxidation, manganese dioxide to manganese sulfate reduction. Given statement is heating sodium iodide with concentrated sulfuric acid and manganese dioxide results in reduction of manganese. Manganese is reduced. This is correct statement and this is wrong statement. Among the species given below, spin only magnetic moment is highest for. In MnCN6 3 minus, here manganese is 3 plus. Manganese oxidation state is 3 plus. Here iron oxidation state is 3 plus. Cobalt is also 3 plus. Here titanium also 3 plus. Manganese configuration 4s2 3d5. What is Mn2 plus? Mn3 plus? Mn3 plus is 4s0 3d4. First remove electrons from outermost shell 4s, after that 3d. Next, iron configuration 4s2 3d6. Now Fe3 plus is what? 4s0 3d5. One electron is removed from 3d. This is Fe3 plus configuration. Next, cobalt. Cobalt configuration 4s2 3d7. Then cobalt 3 plus is 4s0 3d6. 4s0 3d6. Next, titanium. Titanium configuration 4s2 3d2. Now titanium 3 plus. Titanium 3 plus is 4s0 3d1. These are the configurations of their respective ions. Now, highest spin only magnetic moment. Generally, atomic structure or lower level means 4s2, 4s0, 3d4. 3d4 means 4 unpaired electrons are there, like that we will do. But sometimes it won't give correct answer. Sometimes it will match with the correct answer. But correct process is according to CFT. We have to find the magnetic moment and number of unpaired electrons with CFT. Let us see that. Here, octahedral complex. Coordination number 6 means octahedral complex and strong ligand. Octahedral complex and strong ligand. So 3d4. Here 3 electrons, 3 boxes, 3 orbitals, here 2 orbitals. Here 3 orbitals, here 2 orbitals in according to CFT after d orbital splitting. 1, 2, 3 electrons. So that is a strong field ligand. Strong field ligand, then pairing takes place. Pairing takes place. So 2 unpaired electrons here. In this case, 2 unpaired electrons. In Fe3 plus, how many electrons? 5 electrons. Cyanide is a strong field ligand. 1, 2, 3, 4, 5. How many unpaired electrons? 1 unpaired electron. Coming to cobalt. Ammonia. Ammonia is a strong field ligand with cobalt 3 plus. It acts as a strong field ligand with cobalt complex. Total how many electrons? 6 electrons are there. 1, 2, 3, 4, 5, 6. All electrons are paired. Number of unpaired electrons are 0 for this cobalt. Coming to titanium. Water is weak field ligand. Water is weak field ligand. Only 1 electron is there. N is equal to 1. Now, what they asked? Highest spin only magnetic moment. This is possible with highest number of unpaired electrons. So, which has highest number of unpaired electrons? 2 unpaired electrons. Here 1, here 0, here 1, here 2. So, highest magnetic moment for manganese complex. Next, lanthanide ion having 4 unpaired electrons. Neodymium 3 plus, terbium 3 plus, cerium 3 plus, holmium 3 plus. So, these are the configuration of all the 4 lanthanides. Nd3 plus. Nd3 plus means remove 3 electrons from this configuration. Here 2 electrons, here 1 electron. Then it is 4f3. Next, Ce3 plus. Cerium 3 plus. Cerium 3 plus, here 2 electron from D. From outermost shell we have to remove electrons. Then 3 electrons are removed means that is 4f1. Terbium 3 plus. Here 2 electrons, here 1 electron. That is 4f8. Next, holmium 3 plus. Here 2 electrons, here 1 electron. This is 4f10. We have to find which has 4 unpaired electrons. Here 3 unpaired electrons, here 1 unpaired electron. We should find in 4f8 and 4f10. F means there are 7 orbitals. 7 orbitals. 1, 2, 3, 4, 5, 6, 7 orbitals are there. Here also we have 7 orbitals. 1, 2, 3, 4, 5, 6, 7. 4f8 configuration means 1, 2, 3, 4, 5, 6, 7, 8. How many electrons here? 1, 2, 3, 4, 5, 6. 6 unpaired electrons. It is not our answer. Next, 4f10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are paired electrons and here 4 unpaired electrons. So, answer is holmium 3 plus. Next, tetraamine aqua chlorido cobalt 3. Cobalt oxidation state is 3. So, that cobalt is CO. Tetraamine AMM. AMM means ammonia. CONS3 4. Aqua. Aqua means water. And chlorido. So, 1 chloride ion. Because coordination number is 6. Coordination number cobalt 3 plus coordination number is 6, 4, 5, 6. Next, here oxidation state is plus 3. To balance the charge outside, it should have 2 chlorines. This is our complex. This is from thermodynamics. The reversible process, cyclic process is given. Cyclic process graph. Initially P1 V1, its temperature T1, P2 V2, P3 V3, P4 V4. So they asked the relation with W1, W2, W3, W4. Work done of a reversible process. Work done of a reversible process formula minus 2.303 nRT log V2 by V1. In terms of ln, that is minus nRT ln V2 by V1. W1, first work done. W1 is equal to how many moles? 1 mole. So N value is 1. R value 2 calories. And temperature value is not given. We have to substitute as T1 and T2 like that. So W1 is equal to minus N is 1, R is 2, 2 T1 ln final volume is V2, initial volume is V1. Similarly, W2 is equal to number of moles same, minus 2, its temperature is T2 ln final volume is V3, initial volume is V2. W3 is equal to minus 2 T3 ln V3 ln V4 by V3. Final volume is V4, initial volume is V3. W4 is equal to minus 2T4 ln final volume is what? V1. Initial volume is V4. So V1 by V4 from the graph. Now check this relation, W1 plus W3. These two I am adding. Then W1 plus W3 is equal to what we will get? Minus 2T1 ln V2 by V1 minus 2T3 ln V4 by V3. So first option is correct. First option is correct. So in a cyclic process, delta E, delta H is 0, but total work done is not 0. Work done is not 0. Delta E and delta H values are 0. The first ionization enthalpy of oxygen is lower than that of nitrogen and fluorine. So fluorine ionization enthalpy is greater than nitrogen. Nitrogen ionization enthalpy is greater than oxygen. This is the order. This statement is correct. The loss of an electron from oxygen leads to stable half-filled configuration. Oxygen configuration 2s2 2p4. If I remove one electron, minus electron, if I remove one electron, we will get 2s2 2p3 configuration. 2s2 2p3. Half-filled configuration is there. Right. But this is not the correct explanation for that. What is the correct explanation here? Left to right ionization enthalpy increases because the size decreases, but the ionization enthalpy exceptional with half-filled and fully filled configuration. Here nitrogen has half-filled configuration, that's why its ionization enthalpy is greater than oxygen. After removal of electron, oxygen gets half-filled configuration, but for this it is not the reason. Why second ionization enthalpy of oxygen is higher than nitrogen means you can give this reason. After removal of one electron, it is getting half-filled configuration, so it is more stable. You can explain like this. An ideal solution thus formed by Raoult's law throughout the composition range. This is the definition of ideal solution. Throughout its composition range, it follows Raoult's law. Mixture of chloroform and acetone shows negative deviation from Raoult's law. This chloroform CHCl3 chloroform and acetone CH3CO CH3. In between these two compounds, hydrogen bond is formed. Intermolecular hydrogen bonds are formed in between chloroform and acetone. This is one of the important example from NCERT. So when more interactions are formed after mixing compared to individual liquids, in mixture if there are more interactions, that is negative deviation. Next, aniline and phenol. Aniline and phenol mixture. Aniline and phenol mixture. Here positive deviation is given. This is not positive deviation, this is negative deviation. In aniline, intermolecular hydrogen bonds are there. In phenol, intermolecular hydrogen bonds are there. In that mixture, again intermolecular hydrogen bonds only, but the strength of intermolecular hydrogen bonds are more compared to aniline and compared to phenol. The coming interactions are stronger than their individual liquids. So this is negative deviation, this mixture is negative deviation, this mixture is also negative deviation. One of the products formed in the following reaction. Grignard reagent is a cyclohexyl magnesium bromide. This is a Grignard reagent. Break this. Grignard reagent means RMgX, alkyl magnesium halide. So when we break this, we will get R minus. So this R minus is very strong nucleophile and highly unstable. So when any compound with acidic hydrogen is given, it abstracts that hydrogen. This R minus abstracts that hydrogen. So I am taking cyclohexanamine. Here it has two acidic hydrogens. This R minus abstracts the hydrogen from that, and the product is cyclohexane. It is taking hydrogen, it is giving cyclohexane. Answer is 4. Next, boron has maximum covalency of 4. This is correct. Example, BF4 minus. The number of covalent bonds is covalency. Maximum number of covalent bonds formed by a particular central atom is maximum covalency. 4 is correct. Beryllium has 3 valence orbitals. Beryllium configuration 1s2, 2s2. Valence shell is 2s. Valence shell of beryllium is 2s. 2p is 0, there is no 2p. So here 3 valence orbitals is wrong. Or include this 2p, if you include this 2p, total 4 valence orbitals. So once the electron enters into second shell, 2p is also available. 2p is also available, but there is no electron. Total 4 valence orbitals. They are given 3 valence orbitals, that is wrong. In p, 3 orbitals. In s, 1 orbital. Magnesium has maximum covalency of 4. No. Magnesium maximum covalency 6. Magnesium maximum covalency 6. It will give a complex Mg H2O6, Mg H2O6 2 plus. So one complex is there in NCERT. Aluminum has 5 valence orbital. Aluminum outermost shell configuration 3s2, 3p3. 3s2, 3p3. In 3s, 1 shell and 3p, 3 orbitals. Total 4 valence orbitals. Aluminum 4, not 5. Next, a protein undergoes reversible thermal denaturation of its initial state N to D at 60 degrees Celsius. Concentration of both N and D are equal at equilibrium. Okay, standard enthalpy change of denaturation is given and standard entropy change. So N gives rise to D. This system is at equilibrium. That is first point. Next, standard enthalpy change. Delta H naught value is 666 into 10 cube joules. And delta S naught value, standard entropy change. What is the standard entropy change? At 60 degrees Celsius. At 60 degrees Celsius, the temperature is what? In degrees Celsius we should not take, we have to take in kelvins. 60 plus 273, 333. Temperature is 333 kelvins. So at equilibrium, delta Z value is 0. Delta Z naught value also, if it is at standard condition, that is 0. Generally, delta Z is 0 equilibrium, delta Z negative spontaneous, delta Z positive non-spontaneous. Here, the system is at standard condition and the system is at equilibrium, delta Z naught is equal to 0. We have a formula, delta Z naught is equal to delta H naught minus T delta S naught. This value is 0. Then delta H naught is equal to T delta S naught. Now, what we should find here, delta S naught we have to find. So delta S naught is equal to 666 into 10 power 3 divided by temperature 333. This is 2 times. Now, how much will get? 2000 kelvins. This temperature is 2000 kelvins. PCl5, so we have to find the geometries. To find the hybridization, one of the shortcut is half V plus M minus C plus A, half into V plus M minus C plus A. For cations, minus C. For anions, A. The charge with minus charge. Anion charge with plus sign. This is formula for hybridization. PCl5 hybridization is sp3d hybridization and 0 lone pairs. sp3d hybridization 0 lone pair means that is trigonal bipyramidal. Next, BRF5 hybridization is sp3d2 with 1 lone pair. sp3d2 is octahedral. In octahedral 1 lone pair is there means that is square pyramidal. Next, BF4 minus is what? sp3 hybridization. sp3 hybridization with 0 lone pairs, that is what? Tetrahedral. NiCN4 2 minus, here coordination number 4. Coordination number 4 means generally there are 2 complexes. One is tetrahedral complex, another one is square planar complex. This is square planar complex. In general, when there is a strong ligand, it will give us square planar complex. Weak ligand, tetrahedral complex. There is an exception, NiCO4, that is tetrahedral. That exceptions we will discuss in coordination compounds. This is square planar. Trans-but-2-ene, trans-but-2-ene, C double bond O, C double bond C, CS3, CS3, H, H. This is trans. This is trans. This is on treated with bromine and CCl4. Very important concept. This is trans. Addition of bromine is anti-addition. Most of the additions are anti. Very few are syn. Very few are syn. Many additions are anti. Now trans and anti gives meso compound. It will give a meso compound. That meso compound is CH3, HBr, HBr and CH3. Meso compound means there will be a plane of symmetry. It is optically inactive. Achiral plane of symmetry is there and it is meso compound. It is meso compound. And this meso compound Br adjacent. Here Br is at adjacent, Br are adjacent. This is correct. This representation is correct. Bromine adjacent. It is meso. Second statement, cis-but-2-ene. Cis-but-2-ene. Two similar groups on the same side. CH3 on the same side. Hydrogen on the same side. This is what cis form. And this cis form is treated with alkaline KMnO4. Alkaline KMnO4 means base reagent. Alkaline KMnO4 is base reagent. With base reagent we will get syn hydroxylation, syn dihydroxylation. This is syn dihydroxylation and this is cis. Cis syn, same. Here also meso. Trans anti meso, trans syn means opposite terms are there means we will get a raceme mixture. Similar terms are there, we will get a meso compound. And this meso compound is CH3, H, OH, H, OH, CH3. So this is a meso compound. For meso compound, these two OH groups are on same side. Here, these two OH groups are on the same side, OH, OH. So this is HH, HH. Anyway, in meso, bromine adjacent, OH, OH adjacent. So the statement is correct. Both statements are correct. Consider the following reaction sequence and choose the correct option. So taking the given compound pH, C triple bond C and methyl group here. This is with hydrogen, palladium, carbon, which is called Lindlar's catalyst. So this non-terminal alkane with Lindlar's catalyst, it gives cis alkene. That cis alkene is C double bond C, pH, and this is methyl group, and here hydrogen, and this is hydrogen. What is this? This is K. Cis alkene is formed. Now here HBr is added. This is electrophilic addition reaction. If H plus attacks here, this is carbocation. If H plus attacks here, carbocation. So this is stabilized by resonance. So H plus will come here as per the mechanism and Br minus is coming here. Now our electrophilic addition product is, this is pH, this is H, and this is Br, and this is methyl group, this is hydrogen, and here hydrogen. What is this? M. This is M. Now I am taking second part, pH C triple bond C Me. This is given with sodium and liquid ammonia. Sodium and liquid ammonia. This is Birch reduction. This is Birch reduction. In Birch reduction, we will get trans alkene. Trans alkene. The trans alkene is C double bond C. Here pH, and this is methyl group. Here hydrogen, and this is hydrogen. Hydrogen on the opposite side. This is trans alkene. With Birch reduction, non-terminal alkane gives trans alkene. This trans alkene is L. Now here HBr is added with the peroxide. any peroxide, benzoyl peroxide or any peroxide, HBr is added with peroxide, then what happens? It is free radical mechanism. The product is based on free radical mechanism, right? Now, if bromine radical attacks here, this is free radical. If bromine radical attacks here, here radical will get. So, bromine is attacking here, hydrogen is coming here, then C, PH, H, H, and this is C, here H, and this is Br, and this is methyl, and this is what? N. This is what? N. This is radical mechanism and this is carbocation mechanism. Anyway, our first option is K and L are geometrical isomers. K and L are geometrical isomers. This is cis alkene, this is trans alkene. So both are geometrical isomers. This is correct. And K and L are enantiomers. No, they are not enantiomers. Cis trans isomers are diastereomers. Next, M and N are geometrical isomers. M and N are geometrical isomers. No, alkenes do not show geometrical isomers. M and N are stereoisomers. No, they are not stereoisomers. The complex which has facial and meridional isomers, Ma3B3 types of complexes shows facial and meridional complexes. Ma3B3 type of complexes. Here, what is Ma3B3? This is Ma3B3 type of complex, shows facial and meridional isomers. Identify the reactions which gives aniline as the major product. Here with lithium aluminum hydride, we don't get aniline. We will get C6H5 CS2 NH2. Phenylmethanamine, not aniline. With KOH and Br2, RCONH2. This R attacks this NH2 with KOH and Br2, we will get RNH2. Here benzene ring is there, we will get aniline. So here aniline is possible. In B, aniline is possible. Sodium borohydride does not reduce NO2. Next, HCl means just acidic medium. In acidic medium, so break it, here give hydrogen and here give OH. In acidic medium, here hydrogen, here OH, we will get aniline. So in two cases you are getting aniline, B and D. B and D cases you are getting aniline. Sodium borohydride does not reduce NO2. This is Hoffman bromamide degradation. This is reduction of cyanide. So this is our answer, direct fact based. The correct decreasing order of oxidation states of underlined atom in each molecule. In P4O10, this phosphorus oxidation state is +5. You can calculate 4 into X plus 10 into -2. Oxygen is -2 is equal to 0. You can calculate X. X value will get +5. In SO3, sulfur oxidation state is +6. In water, oxygen oxidation state is -2. In H2S, sulfur oxidation state -2. In N2O5, nitrogen oxidation state +5. In N2O3, nitrogen oxidation state is +3. And PbO2, lead oxidation state is +4. And Cl2O7, chlorine oxidation state is +7. ALH3, in ALH3 aluminum oxidation state is +3. Here one important point, suppose barium peroxide is given. Barium peroxide given means what is the barium oxidation state? Not +4 here. This is peroxide. Barium is +2. Alkaline earth metals always +2 oxidation state. So based on this oxidation state, you can arrange them in increasing order. This is based on aldol condensation. This is our compound A and this is compound B. To give aldol condensation, we should have at least one alpha hydrogen. Here no alpha hydrogen. No alpha hydrogen. Right? It should have at least one alpha hydrogen. So what type of products we can expect? A on A, one product, and A on B, one product, And B on A we don't get because there is no alpha hydrogen. Here no alpha hydrogen. Here alpha hydrogen is there. So A can give a product with B, A can give a product with A. AA and AB product. Now first I am taking AA product. AA product, here methyl group, here methyl group. So this is alpha carbon, alpha hydrogen. Assume this OH minus has removed that alpha hydrogen, we will get negative charge. Carbanion. Carbanion is our intermediate. Next, another A is what? Another A is, this is double bond O, two methyl groups. This carbanion attacks here. This carbanion attacks here. This pi electron shifted to oxygen and it will become O minus. That O minus abstracts the hydrogen removed from here. Now our product is two methyl groups, no change here. This double bond, no change here. When it attacks here, this negative charge is attacking here. Now we will get a compound like this. Here two methyl groups, and this is OH. Next, on heating, from here OH and from here hydrogen is removed, water is removed, condensation takes place. This is aldol. Now condensation takes place, double bond is formed, and that double bond product I am writing here. Double bond O, two methyl groups, no change, and this is double bond, cyclopentane ring, and two methyl groups. Where is this product? This is our product. This is AA. Now I am taking AB. AB aldol condensation. A on B. Same carbanion, intermediate, minus double bond O and two methyl group. And this is with benzaldehyde. Now this carbanion attacks this carbon, will get an aldol. That aldol is this is O, CH, OH and pH. It is on heating. From here OH, from here hydrogen is removed. Then double bond is formed. The product is this double bond, CH and pH. It is like cis form. It will give a trans form also. That is stereo part. So this product is possible. This product is possible. 2, 3, 4 is possible. 1 is not possible. Among the following compound having conjugated double bonds. First one I will verify. Hepta means 7 carbons. 1, 2, 3, 4, 5, 6, 7. 7 carbons. 1, 2, 3, 4, 5, 6, 7. 7 carbons. First carbon double bond and third carbon double bond. Remaining all are single bonds and it is balanced with hydrogens. That valence is satisfied with hydrogens. Now this is conjugated. Double, single, double. This is called conjugation. In others, no conjugation. Here only conjugation. Oxidation of para-nitrotoluene. This is toluene, para position nitro. This is oxidation. This is oxidized with acidified potassium permanganate. This CH3 is oxidized to COOH group. This is oxidized to COOH group. No change in NO2. What happens here? This NO2 group increases the acidic character. NO2 group is strong electron withdrawing group, minus M effect. This minus M effect increases the acidic nature. Next, reduction of para-nitrotoluene. This is our toluene. Here NO2 is. This is para-nitrotoluene. Reduction with tin and HCl. This NO2 group is reduced to NH2. Para-amino toluene will get. This NS2 is what? Plus M group. Positive mesomeric effect. Electron donating group through resonance. So this is NS2. So aniline is a base. Here methyl group has hyperconjugation, positive hyperconjugation. This positive hyperconjugation effect increases the electron density in the benzene ring, so basic nature increases. What they have given here, reduction of para-nitrotoluene with tin HCl followed by neutralization gives an amine that is more basic than aniline. Correct. This is more basic than aniline. And this is more acidic than benzoic acid. Correct. Electron withdrawing effect increases the acidic nature. Electron donating effect increases the basic nature of amines. The green paramagnetic species formed by heating KMnO4. When KMnO4 is strongly heated, we will get potassium manganate. This is potassium permanganate. This is potassium manganate. Along with that, we will get manganese dioxide and oxygen. Manganese dioxide is black powder. Manganese dioxide is black powder and potassium manganate is green color. This is green color. So K2MnO4, KO2 and others won't be formed. MnO2 is formed, but this is black, not green. Next, Attard reaction. This is Attard reaction. This toluene is treated with chromal chloride, CrO2Cl2, CS2 in water, acidic medium. It produces benzaldehyde. It produces benzaldehyde, Attard reaction. On treating compound P, saturated sodium bicarbonate solution, brisk effervescence is observed. This is wrong. Benzaldehyde does not react with sodium bicarbonate. Benzoic acid reacts with sodium bicarbonate. The compound P can be, this is P. The compound P can be prepared by treating benzene with anhydrous AlCl3 and acetyl chloride. Friedel-Crafts acylation reaction. This is benzene taking acid chloride CS3COCl, AlCl3. This AlCl3 abstract with chlorine. CS3CO is our electrophile. It substitutes the hydrogen. We'll get acetophenone. We are getting acetophenone, not benzaldehyde. So this is wrong. This statement is wrong. This statement is wrong. On treatment with bromine water, compound P gives a white precipitate. Benzaldehyde does not react with bromine water. Here CHO is electron withdrawing group. It decreases the electron density. When electron density of the benzene ring decreases, it does not allow Friedel-Crafts reactions. The rate of electrophilic substitution decreases with electron withdrawing effects. Coming to fourth one, compound P is obtained by hydrogenation of benzoyl chloride with palladium on barium sulfate. This is Rosenmund's reduction. Taking benzoyl chloride with palladium, barium sulfate and hydrogen. Hydrogenation with palladium and barium sulfate. So Rosenmund's reduction, this Rosenmund reduction gives benzaldehyde. So this compound is P is formed. Next, 1:3 electrolyte in an aqueous solution. When this complex is dissolved in water, this complex ion splits into CO NH3 3 plus 3Cl minus. Here one complex ion is formed and 3 simple ions are formed 1:3. This complex ion does not break. In aqueous solution it is not going to break. So 1:3. Consider the following schematic plots of orbital wave function psi r against distance from the nucleus. The figure representing the two radial nodes. When the curve touches the x-axis, on x-axis it is 0. The radial distance is 0. Sorry, wave function is 0. On x-axis, that wave function psi r is 0. So where it touches the x-axis, that is radial node. Here no radial nodes. Here one radial node. Here two radial nodes. Here it is touching. Here it is touching. Two radial nodes. D, graph D is this one. Here no radial node. Here one radial node. Here two radial node touching two times x-axis. And here this graph is this one radial node. So two radial nodes is for C. Arrange the following compounds in the increasing order of polarity. Acetic acid polarity is more. There is CS3, C double bond OH. This carbonyl group is there. Its polarity is more. Acids are more polar. Next, alcohols. Alcohols are more polar. CS3, CS2OH. Alcohols are more polar. Next, from this, ketones. Next, ketones are more polar. CO group is there, polar, but this alkyl group and this alkyl group reducing the polarity of CO group. Electron deficiency of this carbon is slightly reduced by this methyl group. That's why polarity is less. After that, ether. Ethers are almost nonpolar, slightly polar, almost nonpolar. It's the highest occupied molecular orbital. We used to say HOMO. Highest occupied molecular orbital. Ne2. Ne2 means there are 20 electrons. This 20 electrons configuration is sigma 1s2, sigma star 1s2. Our configuration greater than 14 electrons configuration we have to write. Greater than 14 electrons configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and sigma 2pz2, pi 2px2, and pi 2py2. Pi star 2px2, pi star 2py2, and last orbital sigma star 2pz2. Total 20 electrons, maximum 20 electrons. MOT is applicable only for 20 electrons. Right, this is the configuration. They asked highest occupied molecular orbital. So all these are occupied molecular orbital. Here electrons are there, here electrons, 1s electron, 2s electron, 2p electron, in all these orbitals electrons are there. So highest occupied molecular orbital means the occupied molecular orbital with highest energy. The occupied molecular orbital with highest energy, that is sigma star 2p. This is the highest energy molecular orbital with occupation of electrons. They may ask LUMO, least unoccupied molecular orbital. Least unoccupied molecular orbital means here 0. No. Means we have to take the unoccupied molecular orbitals in all of them which has lowest energy. First one we have to select. Here last one, there is first one. Thank you.